So for the typical reaction of type 2 carbonyl, we're using an ester here. This is an ester. In the reduction reaction, using lithium and aluminum hydride, of course, followed by water. Remember, notice these are two steps. You can't mix water and lithium aluminum hydride all in one round bottom flask. That's going to lead to an explosion. So a violent reaction. So in this case, let's begin talking about the mechanism. So we have lithium aluminum hydride. You know that the first step is the attack by the hydride, of course, as this hydrogen here and its electrons. So that's the addition. So we have the CH3, C, OCH3, and of course the H that we just added. Now, this is not going to simply now go to the second step and get protonated. So this step right here, or this product, okay, is going to undergo another reaction, another change. And let's show you that one. We already talked about this, but let's show you. Okay, so the H added, remember, is a bad leaving group, but let's look at the OCH3. So we know that H minus and CH3 minus I'm talking about this H and its electrons and this CH3 and its electrons. Those would be bad leaving groups, okay? They are very, very bad leaving groups, or let's say they cannot leave. They can't leave. However, the OCH3 can leave. So what's going to happen is the following. These electrons, the oxygen, are going to come down and then kick, let me erase this underline here, kick the OCH3 out. So this is now an elimination. Oops, let's use a different, same color. We're just going to call it elimination. So now look what you have now. You have H3, OH. So you arrived at an aldehyde. Right here. Problem is you think, okay, that's it. I'm going to stop. I'm done. No, it won't. So what's going to happen is aldehydes, this one right here, this aldehyde is more reactive than the ester. So that means it will continue the reaction. So we have now the aluminum hydride. Attack We're going to write it down here. So that's another addition reaction. Notice what's happening here. Addition, elimination, now back to addition. And it's basically like, you should be able to see it now. Basically like the reaction we did on the last page involving the aldehyde. Let me show you really quick before. It's this one. Imagine now you started here. This is what happened as you continue. Of course, now the next step is protonation. That's where water comes in. And of course, you arrived at an alcohol. So be aware of that. Make sure you remember what are you going to end with. So in this case, you have an alcohol. You have a primary alcohol. Addition, elimination, then followed by an addition. So the reaction will keep going until you arrive at an alcohol. Very well. So remember, there are no leaving groups here. So the question is, I understand there might be a contradiction now. Some of my students may say, how come in last semester we said OCH3 was a bad leaving group? How come now it can leave? We did say that when we talked about SN1, SN2 reactions and E1, E2 reactions. So that's very true. But let's look at why it could act as a leaving group. So if you have a nucleophile, this was an SN2 reaction, attacking the sp3 hybridized carbon as OR, in this case, the alkoxide as a leaving group. We said there's no reaction in this one. So basically, if you were to show this, you would say the nucleophile is right here. You have C. And H. And the reason why this does not form is because the product and the reactant have similar energy. So the reaction is not going to take place. So product So remember, the whole idea of a reaction taking place is that you want to go to low energy. So if this had a lower energy, significantly lower energy than this, then the reaction takes place. But if they have the same energy, it's like going from this to that. And you basically don't see this in chemistry. It has to be something like this as an exothermic reaction. This is the reactant, this is the reactant, this is the product. So we're here. That's why the alkoxide is not a good leaving group in an SN2. However, when it comes to this, the alkoxide there's a good reason for it to leave, because if we draw the electrons here, and these electrons come down, alkoxide would leave. You would form And the reason why this happens is because this is an aldehyde and this is a tetrahedral intermediate. The aldehyde is much more stable than tetrahedral intermediate. Which is this. Bond energy of the carbonyl group is so high. So tells you that that's how much it can be stabilized by 179 kcal per mole. So it's willing to take that risk to expel that group to achieve an aldehyde, which has a carbonyl group, and the bond energy is so high that again it would again make it relatively more stable than the tetrahedral intermediate.